So exam 1, first order of business, is Friday, February 12th. So a week from this upcoming Friday. And all the questions will be based on assignment questions up through, so you need to understand the assignment questions through, what would that be, February 5th. So a week before. And the next, the questions after 2-5 will be on the next exam. And then, okay, any questions about the test? After you take the test. I don't know if that helps as much, but.
Well, he clearly hasn't written the test yet.
Yeah, obviously. Right. If you asked me at like 11:30 in the morning on the Friday of the test, I still could not give you the answers to the test.
Because you still haven't made it.
Right. Or at least I haven't solved it yet. Any other questions about the test? Yep.
Can I have more of the kind of stuff we're getting on this assignment quizzes with just the theoretical stuff, seeing we understand the theory as well?
All of the kinds of questions that have been on the assignments, those are the kind of questions that will be on the test. So nothing will be like a drastically different way of thinking about it than what you've seen. No, none of that. So I'm just doing that on the quizzes this time. So it's just problems.
How many problems will be there?
It depends on what kind of problems it is. I will try not to. It's only 50 minutes, so I can't put that much on there. I don't want to make it like a race against the clock. I'll try to make it about a 40-minute test or something for most people. So hopefully half the class will hand it in before the class, So I'll try not to make it take too much time. Any other questions about it? And then on Friday there was that thing. I guess I won't go through the whole derivation, but you asked that question about where does the Q transpose come from. So on Friday, the question was where does that second, when you're representing a vector in a new coordinate system, you just left multiply one Q matrix. So where does this second Q transpose come from with tensors? With stress transformations.
Does it work for the strain, void strain?
No, that's a good question. So that's an important thing to recognize is we don't have any way to re-express strains. They don't rotate. They're not tensors. So what you have to do is re-express the stress and then recalculate the strain. Just use the compliance matrix again to recalculate the strain. Yep.
Quick question. Did we get a note sheet on the exam?
I'll give you all any equations you need. Yep. And if there are any that I forget to put on there, which happens every time, then I'll write it up on the board.
Did you just put the compliance matrix on it?
Yes, compliance matrix. That will be on it. Okay, so where does it come from? Here's the basic idea of the argument. We know that We know that the oh no, here. Sorry about that. We know that the stress tensor in the new coordinate system times the normal vector in the new coordinate system is equal to the traction vector in the new coordinate system. Okay, and so what the thing that I posted in the news items, what it does is, so we know that has to be the case, and we're going to show that Q times the stress tensor in the old coordinate system times Q transpose times the normal vector in the new coordinate system is equal to the traction in the new coordinate system. Okay, so if this if Q sigma Q transpose is equal to sigma nu, you know that this has to hold. And so that's what I showed. Just went through a couple steps. And if you follow those steps, it's not just that, like, okay, I believe you or whatever, but it helps you see where, like, if you follow the steps, you can actually see where that Q transpose comes in, you know. So if you don't care about it, don't read it. If you're interested, you can look at it. Any questions about that? All right, so last time we were talking about principal stresses. And the setup was we want to find a scalar lambda and a unit vector n such that the stress tensor times n is equal to lambda times n. Then lambda is an eigenvalue representing a principal stress. And n is a corresponding eigenvector representing a principal axis. If you take this equation and rearrange it, you come up with this form: sigma xx minus lambda, and then the two shears on the x face, and sigma xy, and now the next normal stress is sigma yy. Take that minus lambda, and then sigma yz. And then on the z face, you have xz, yz, and zz minus lambda. And this is all multiplied by nx, ny, nz, and it has to be equal to 0, 0. This requires that the matrix on the left is non-invertible. And one thing, if a matrix is non-invertible, you know that its determinant has to be equal to 0. So in order to have a solution for this, it requires that the matrix determinant is 0. Okay, so we need to know how to take a matrix determinant. So if your matrix is A, B, C, D, E, F, G, H, epsilon? No, not really. I'm going to call it I, even though you're not supposed to do that. I already called one E, so. Okay, so the matrix determinant, and you draw it as like absolute value of this matrix. You can calculate this way. A times EI minus HF minus B times DI minus GF plus C times D, sorry about that, D, H minus G, E. Or you could also do it, so the way that I've done that is for each one of these, so we start out with one that's multiplied by A. So cross out the column and the row that A are a part of, and then take this minus this to multiply it by. And when you do the one in the middle, you have to have a negative sign because y always has to be difficult. You can also do this as A times EI minus HF minus D times, do the same kind of thing, BI minus HC plus G times BF minus EC. And you can actually do it with any row or column. There's some things you have to worry about, but those are good enough for us. And anyways, your calculators, I think all your calculators are calculate determinants for you. If they don't, come talk to me and we'll make a program that does it. So you don't ever have to calculate that yourself. All right, so let's think about the determinant of this thing. So take the determinant of, let's call this matrix here star. So you get sigma xx minus lambda times sigma yy minus lambda sigma zz minus lambda minus sigma yz squared minus sigma xy times the quantity sigma xy times sigma zz minus lambda minus sigma xz times sigma yz and then plus sigma xz times the quantity sigma xy sigma yz minus sigma xz times quantity sigma yy minus lambda. And for this to be, for that matrix not to be invertible, this has to be equal to 0. So in general, this problem is finding the 3 roots that you get from setting a cubic polynomial equal to 0. Okay, so you get three roots for lambda. The last thing you want to do is we don't just want to know those principal stress values. We want to know what the coordinate system is where those are the stresses. So to get the coordinate system axes, after you have the 3 values for lambda, one by one, plug lambda into this equation. Times that normal vector, set it equal to 0. And solve for the unit normal vector corresponding to that lambda value. So what you get out of this problem is you get 3 lambda values that represent the principal stresses and 3 unit normal vectors corresponding to the coordinate system axes where the lambdas are the stresses. Okay, so mainly you're just going to plug this into MATLAB or plug it into your calculator, and it's going to do all this stuff for you. But let's do 2 calculations by hand. So let's say that the stress is equal to 3, 0, 0, 0, negative 5, 0, 0, 0, 0. So first, what are the principal stresses? And second, what is the principal coordinate system? And this is, well, do you remember what the definition of principal stresses is? What are we looking for when we do a principal stress problem? We're looking... Yeah, well, we're looking for a coordinate system. Basically, we're looking for a coordinate system orientation where there are no shear stresses. All the stresses are normal stresses. Okay? We're looking for that coordinate system, and then we're trying to figure out what those stresses are that are only normal stresses. Well, this one's already done for us, right? Because this only has normal stresses. So when we do this eigenvalue, eigenvector problem, we should get a 3 and a negative 5 and a 0. And it should tell us that the coordinate system axes are our original ones. So we expect to get, and these are usually, people usually talk about these as sigma 1 is the maximum. Sigma 2 is the middle one. Sigma 3 is the minimum.
Isn't sigma 3 the negative 5?
Yeah.
Or sorry, sigma 2.
Oh, usually people, you can, arrange them in any order, as long as you have the right axis corresponding to the right one. So let me show you how that works. So in other words, they're just they're arranged in order of biggest to smallest. They're not arranged according to X, Y, and Z. Because you could, so this is in a coordinate system like this, with the z-axis coming out. If you rotated this coordinate system 90 degrees, then that 3 wouldn't be the x anymore. That 3 would be the negative y. And so, so the order of those things can change around without changing the meaning. What matters is that each one of those corresponds to the correct axis. So we expect the principal stress of positive 3 to correspond to 1, 0, 0. We expect the principal stress of 0 to correspond to 0, 0, 1, because that's the z normal stress. And we expect sigma 3 to correspond to 0, 1, 0. And I'm just going to go through this calculation. Any questions about this setup? Okay, so to find the lambdas, we have 3 minus lambda, 0, 0, 0, negative 5 minus lambda, 0, and then 0, 0, 0. And we're taking the determinant of that. Determinant of that. Oh, no, this shouldn't be 0 here. This should be minus lambda. 0 minus lambda. Okay, so the determinant of this is 3 minus lambda times the quantity negative 5 minus lambda times 0 minus lambda, and then minus 0. Then you got minus 0 and plus 0. And this has to be equal to 0. So we have 3 minus lambda times the quantity 5 lambda plus lambda squared. We're setting that equal to 0. So we know one of these roots is 3. And we can, we can factor this out into 3 minus lambda, lambda, and 5 plus lambda. Okay, so one of these roots is equal to 3, if that one's equal to 0. If that one's equal to 0, lambda is equal to 0. And if that one's equal to 0, lambda is equal to negative 5.
Is there a reason that you multiply what was inside together? Because it seems like it's already just factored into the roots.
Yeah, that's true. I'm just used to doing that.
Oh,
Yeah.
But there's like, is that
There's no
like
reason, no.
Or if we know
Well,
it's
you're gonna most of the time you're gonna have to. This was already factored just because we didn't have any. Like normally you'd have stuff here that complicates it all.
Right.
But yeah, you're right. In this case, it was already factored for us. Okay, so now we have to figure out the coordinate system axis directions. Okay, so we have the principal stresses. And now we want to find the corresponding axes. So I'm going to start with lambda equals 0. Well, let me just go in order. So lambda equal to 3. And we're going to find the axis corresponding to lambda equals 3. So we have 3. The way we're going to do this is we're going to plug each of those lambda values into, so let me write this out. So we got 3 minus lambda, 0, 0, 0. Negative 5 minus lambda, 0. And then 0, 0, 0 minus lambda. And we're multiplying that by 3 unknown values, 3 unknown components for the principal axis. It all has to be equal to 0. And so what we're going to do is we're going to take this 3 and plug it in for lambda. And then we're going to solve for those 3 unknowns. So we have 3 minus 3, 0, 0, 0. Negative 5 minus 3, 0, 0, 0, minus 3. So that's 0, negative 8, 0, 0, 0, negative 3 times nx, ny, nz. And that gives us 3 equations. The first one says 0 equals 0. That's not helpful. The second and third will be better. The second one says negative 8 ny is equal to 0. And the third one says negative 3 nz is equal to 0. We want a unit vector that satisfies those 3 requirements. Well, we know that ny has to equal nz has to equal 0. So there are only 2 possibilities for a unit vector that meets these criteria, positive 1, 0, 0, and negative 1, 0, 0. And we can choose either one of those we want. Or negative 1, 0, 0. And no matter which one of those we choose, obviously to match it up to what we started with, we'd want that x-axis to be 1, 0, 0. But we can choose the other one and everything will work out fine. Everything will still make sense. All you have to do is make sure that the 3 unit vectors you choose satisfy the right-hand rule for the axes. You know, the x-axis crossed with the y-axis has to be equal to the z-axis. X cross z has to be equal to y, and y cross z has to be equal to negative x. Those are the only 3 requirements. Okay, so let's choose this one and move on to the next eigenvalue. Any questions yet? And yes.
So maybe I missed something. I'm sorry. But if this only applies to like certain types of things, right? Where because there can be some where there's no way to rotate the coordinate system to avoid shear.
No, it's an amazing fact. But every stress tensor, if you find the right coordinate system, there's a coordinate system where there are no shear stresses. And as if that wasn't, that would only be sort of a strange fact, except for the fact that when you find that coordinate system, the stress elements that you have are the biggest possible normal stress, the smallest possible normal stress, or the most negative, and then one in between, which are, the one in between you don't care about, but the maximum and the minimum are really important values. So it's weird that it works out, but it's always the case. Okay, so now let's do it for, the next one is for lambda equals -5. So our problem is -5, no. It is +3 minus -5. 0, 0, 0. -5 minus -5. And then 0, 0, 0 minus -5. Times nx, ny, nz is equal to zeros. So that's +8, 0, 0, 0, 0, 0, and then 0, 0, +5. Times nx, ny, nz. So the three equations that you get from this are +8 times nx is equal to 0. 0 equals 0. And 5nz is equal to 0. And so the requirements say that nx is equal to nz is equal to 0. So your options are 0, 1, 0, or 0, -1, 0. I'll take that one.
Is there a reason you're choosing the positive one just because it's easier?
Yeah, just because it's easier. Maybe I should have chosen the negative and we could see how it works out, but
You have like negative, positive, negative.
yeah, we could do that.
That would still work.
Yeah, let's do that. So
No matter what,
now that you've already written this down, let's,
no matter what you choose, like any.
I'll show what you would have to do if, so now it's not going to exactly be the coordinate system that we had before, and I'll show how we have to, what we have to do to make it work as a coordinate system as a stress tensor. Okay, so let's do the last one. So lambda is equal to 0. And so you have 3 minus 0, -5 minus 0, and 0 minus 0. Nx, ny, NZ is equal to zeros. And so that's 3, 0, 0, 0, negative 5, 0, 0, 0, 0 times nx, ny, nz and the three equations that this gives us is 3nx is equal to 0, negative 5ny is equal to 0, and 0 equals 0. So nx is equal to ny is equal to 0, and so our axis is equal to either 0, 0, 1 or 0, 0, negative 1. And let's take the negative again. Okay. It's arbitrary, but we'll take that. All right, so now let's look at what our coordinate system looks like. Our original coordinate system was this one. And we found the new principal coordinate system that has the following axes. And I'm not going to choose them yet, but it has, I'm not going to name them yet, but we know we have one in that direction, one in that direction, and one in that direction. And now we have to label them in a way that meets the, we need I cross j equals k. I cross k equals negative j, because y always has to be the difficult one. And then j cross k is equal to I. That's what we need when we label these. And there's multiple ways you could do it. So let's make this the x-axis, this the y-axis, and that the z-axis. Based on this choice, of x, y, and z, our sigma xx so our sigma xx is the one with the eigenvector that's equal to 0, 0, negative 1. That's that third one we did. And so the stress is 0. So what you're going to do is go back to the eigenvector calculations and choose the lambda associated with each axis. So that's how we got that one. Our y-axis is 1, 0, 0, so we have to go back and find where that was, and that was the first one we did. 1, 0, 0. And that corresponds to lambda equal to 3. So our new y stress is equal to positive 3. And then for our ZZ, so that is the one that's in this coordinate system is 0, negative 1, 0. And that's negative 5. Okay, so I want to do one more thing. I want to draw the stress cube associated with this. And you'll see that all these random numbers make sense with what we had before. So here's our stress element. And our coordinate system has y that way, x that way, and z down. Okay, so on our positive x face, which is in the back, we have, well, nothing. So there's nothing to draw there. On our positive y face, which is this, we have positive 3. And on our positive z face, which is underneath, we have 5 pointing in, which means on the one we can see, we also have 5 pointing in, but that's the other direction. So it looks like that. And what would we have gotten at the beginning if we would have drawn this stress cube? We would have gotten three, 5. Oh, yeah! That's awesome. Like even with all, like fiddling with all the axes, using negatives or whatever, it means the same thing. Okay. Any questions about that? So next time, I'll let you do a couple examples. And all of the calculation part of this, the nice thing is that's the part your calculator does. But you do have to be able to interpret those directions that way. So that's what you'll need to get comfortable doing. Okay.